Okay, so hopefully now you have a little bit of an idea about what we're trying to do when we construct the tangent space. So now let's go through its construction with a bit more detail. So as before, of course, we begin with a manifold. Now I'll just draw it quite simply. Then we're considering a particular point in the manifold around which we want to construct the tangent space. So, as before, we begin by constructing our set of all the smooth curves which we can draw through the point P. Just draw a few of them here. Now I'm going to call each of these curves phi, and they're parameterized by lambda. So now I need to start writing things down. Phi is a map from the real numbers to the manifold, which maps our lambda parameter into the image of the curve. That's all well and good. So now this image of the curve lives in the manifold. It's a set of points on the manifold. We kind of can't really talk about it concretely unless we work in a chart. So now that's what we want to do. We want to find the image of this curve in some particular chart. So I'm going to use a chart which I'm going to call X. So you'll now remember that the chart map is just mapping the manifold into some subset of the real numbers. So just to keep things super simple right now, I'm going to say that the manifold is two-dimensional. Without loss of generality, you can just extend this to any arbitrary dimension. Just to keep it easy to draw, I'm going to stick with 2. So our chart map then is going to have two coordinates, x1 and x2. And now, of course, this phi is going to have some image in the chart. So it might look like that. And then, of course, the point P is going to appear in the chart also. Okay, now, so maybe one other subtle point which I want to just define now. We want to define our curves in such a way that when the parameter is equal to 0, we are given the point P. This just simplifies things. So if we take phi of 0 to be P, okay, so this is fine. We've seen all of this before. We just have a manifold. We've given that manifold coordinates using a X chart, and now we're considering some set of points in our manifold. It's a curve, and then we're looking at how that curve appears in a particular chart. So now, already, you can probably guess how we're going to construct the tangent vector to this curve. It's going to make a lot more sense for us to work in the chart because we understand really well how things work, because this is just R2. It's easy to do calculus on R2. So we're going to like to work in the chart and then somehow translate our results back to the manifold. So, of course, the way to translate back to the manifold is with the inverse of the chart map. So just X inverse. Okay, so we've seen all this before. We know how to construct a manifold, give it coordinates using a chart, and now we're just simply considering some curve or subset of points in the manifold and considering its image in a chart. Nothing new yet. Now, to continue in constructing the vector, we're going to need a final piece. This might seem a bit strange to begin with, but once you've seen the full construction, it will make sense why we need this. So I encourage you to stick with it and maybe re-watch after you've seen it the first time, and it might make more sense. So to define a vector, we first need something for the vector to act on. Now, why is this? Well, we've seen previously that a vector should be realized as some kind of linear map. So it needs to map from somewhere into somewhere. So the object which we're going to map, or we're going to feed into the vector rather, is just going to be a function on the manifold. So I'm going to say we have some function f which just maps to R, and this f is going to be in the set of smooth functions on the manifold. And I also want to do is restrict this function, or essentially just evaluate the function along one of these particular curves. So I want to restrict the function to a curve. I essentially just evaluate the function on the argument of the points which lie on the curve. So I'm just evaluating the function after the curve. And now, once we have this, we have everything that we need to construct the tangent vector of this function along the curve. So that's what I'm now going to define. So I'm going to say the tangent vector, which I'm going to call v, to the curve, so I'm going to give it a subscript phi, and now this vector has to act on something. We'll see much more of this shortly, but it's going to act on the function. Just take this for granted for now. And now I'm just going to simply define this for you as the parameter derivative evaluated at the parameter is 0 of this thing here, the function evaluated on the curve. So this might look nothing like any sort of vector that you've seen before. We'll do some massaging of this expression to get it into a more kind of familiar form. But for now, let's just kind of think about what it means. Essentially, what it's saying is that the vector is some kind of differential operator. It's a derivative that's acting on this function, and what it's going to produce is essentially the directional derivative. That's sometimes the terminology we use here. So the vector is a derivative. The vector kind of depends on the curve. And now we're going to discuss this more in a future video. These curves are known as integral curves, and each of these integral curves can sort of be thought of as giving rise to each of these vectors as a differential operator. More on that later. But for now, we're just going to think of the vector as kind of acting along the curve direction on the function. And now, because the function is just completely arbitrary, you sometimes just leave the function out and just talk about the vector as kind of a differential operator waiting to act on something. Okay, so let's try and digest this expression a little bit more and make a bit more sense out of it. So at the moment, we're trying to take this parameter derivative, and it's kind of very buried inside this function here. So let's write this in a bit more of a suggestive form now, using the chart map. Essentially, we want to kind of eliminate the need for this phi. We want to just work entirely in the chart and not on the manifold. So how would we go about doing this then? Well, essentially, we're trying to evaluate the function on the curve. And now if we can be a bit sneaky here and rewrite the curve in terms of the chart. Okay, so we want to consider mapping the points on the curve which lie in the manifold using this function f, but we want to do this using the chart, so we essentially want to find a way to talk about these points in terms of points in the chart. Okay, so now if I start calling the curve in the chart, this is going to be x after phi. So this is, if we trace back where we're coming from, we have our parameter lambda. So this map x after phi is mapping you from the real numbers lambda. It first takes you into the manifold using the map phi. So you're first taken into M, and then you're taken into R2 or RD using the map X. So it maps the parameter lambda to the image of the curve, and then the image of the curve is mapped to something new, which is essentially the image of the curve in the chart. So I'm going to give that a name. I'm going to call that x mu of lambda. Space a bit there. So I'll just go through again what I did because it's a bit strange. Essentially, I'm tracing all the way back, starting from the parameter lambda, which we remember comes from the real numbers. That feeds into the phi function, which gives us a particular subset of points or a curve in the manifold. So that takes us to here, and then we map that phi using x into the chart. And now I'm calling the image of the curve in the chart x mu of lambda, where the x mu just is kind of used to refer to each of the individual sort of coordinate components of this multivariable function. Okay, so that's just a really roundabout and fancy way of getting an expression of the curve in terms of coordinates. Okay, so now let's just remember what we're trying to do. We're trying to map this phi curve using f. So essentially we're trying to compute the action of the map on the curve. Now we've already seen that the curve has an image in the chart. We could consider translating this chart image back onto the manifold. So if I now just write that phi of lambda is equal to the inverse chart map of its chart image. So that's x inverse after x mu of lambda. And now I can finally write down that the function acting on the curve in terms of the chart variables is this expression. Okay, so you might be wondering, well, what's the point of doing all of this? Aren't we essentially just writing down the same expression but with a factor of the trivial identity in there, because the inverse function acting on the function is just the trivial identity? Well, yes, but if you've taken any sort of quantum mechanics course, you know you can pretty much solve any problem by inserting a factor of unity. We're kind of doing something similar here. It's just trickery to get us into the chart so we can calculate things in the chart and then move back to the manifold using the inverse function. So all of the calculations actually happen in the chart, nothing happens on the manifold, but we just go backwards and forwards between the chart and the manifold using this x. So how is this useful then? Well, this expression allows us to easily compute this derivative now. So if I rewrite this in a more suggestive form, so I'm saying f after x inverse after x mu of lambda. Okay, and now we realise this expression is equivalent to this, so we can just simply substitute and take the lambda derivative. So I'm actually going to rewrite this to give myself some more space. Okay, so I'm just rewriting what was there. It was the vector attached to the curve phi evaluated on the function is this lambda derivative of the function eating the curve, all evaluated at the point in question. So that's our vector or directional derivative. Now I'm going to use this expression with this expression to get an expression for the vector in terms of its coordinates. So I simply need to substitute this into here. So we get the derivative with respect to lambda evaluated at 0 of, now this kind of rather complicated looking thing, f after x after x of lambda. Now this might look hideously complicated, but the derivative is actually really easy. So I can write this whole thing as simply just the derivative of the first function in the composition with respect to the second, so maybe if I put brackets around that, these are our two functions. We could call that capital F, capital X, if it makes it easier for you. So just really quickly, this is the chain rule. For taking the F derivative with respect to lambda. Hopefully you've seen this before. Okay, so I'm going back now, taking the derivative with respect to x mu, dx mu, and then with respect to the parameter, all evaluated at the point in question. So now we're almost there, we just need to make a few realizations. What does f after x inverse mean? Well, it's essentially the function after you've taken this x mu through the x inverse. So this is essentially just the function acting on the image of the curve. So now all of this is easy to calculate. This first thing is just df by dx mu, and then this is just dx mu by d lambda. So I'm going to rewrite this now, this, in a slightly more suggestive way. I'm not changing anything, I'm just writing terms in a different order. Okay, so this expression is identical to this expression with this definition down here. So now we can start to identify a few things. This dx mu with respect to the lambda derivative, these are what we commonly call the components of the vector. So I can give them now a different name. I'm just going to call them capital V superscript mu. So this whole thing is V mu. So these are what are commonly referred to as the components of the vector. You can essentially understand what they are now. They're just the parameter derivatives in each of the coordinate directions. So for example, this curve up here, it's going to have, the curve is kind of pointing along the x1 direction, so it's going to have a large derivative along x1 and then maybe a very small derivative along x2. These are what these dx mu by d lambdas are going to give us, and just evaluated at the point 0 to give their values at the point P. And now this d by dx mu object is something which might look a little bit strange. It's just a partial derivative not acting on anything. Now this gets an abbreviation partial derivative with a subscript mu, and this is what forms the basis of the tangent space. So of course the tangent space is a vector space, it must have a basis, and the basis for that space is given by these partial derivative operators. So this whole thing here in the white brackets is the vector, and the vector, this v mu d mu, acts on a function. So now this lines up with our previous discovery that a vector should be a linear map. It has to map some kind of object to produce any tangible results. Thinking about the vector without an argument, it kind of feels incomplete. It's a derivative not acting on anything. The vector is a linear operator. It has no intrinsic meaning by itself. It needs to act on a function to give a definite answer. However, since the function we wrote down here was just completely arbitrary, we don't need to even write it down at all, and we can just talk about the vector abstractly now in this way. So this expression now turns out to be extremely powerful because it gives an abstract and also coordinate-free way to talk about the vector. Notice writing d mu like this, we're not talking about the coordinates yet. We can use this expression to talk about the vector in any coordinate system just by writing d mu and then whichever coordinate system we want to use. So we'll see in the next section how we can use this to transform. We know that we can just change charts, so the vector should have a representation in some other set of coordinates. Okay, so I'll just summarise what we've gone through now then. It was a rather complicated construction. There are a lot of different parts, so I'd encourage you to go back and revisit if you're confused. So we began with a manifold. For our purposes, I said it was two-dimensional, it could be any dimensional. We then wanted to construct the tangent space at our point P. So to do that, we had to first consider, or just create, the set of all smooth curves that pass through the point P. Then once we have this set of all of our smooth curves, each of these smooth curves is going to give rise to a vector field, or a vector rather, at the point P. Then by evaluating that vector, which we've now realised is some kind of derivative operator, by evaluating that on a function, we can understand the action of the vector. It produces essentially the tangent to the curve at that point. So now one thing I probably forgot to mention and should have really emphasised is that what we're considering here is the algebraic structure which is generated by these partial derivative operators. So essentially another way to state what the tangent space is we can say that it's the vector space which is spanned by these partial derivative operators. So essentially these partial derivative operators which come from a particular chart, they create a vector space on the manifold just from the fact that we've given the manifold coordinates. So by giving a manifold coordinates, we're sort of immediately led to discovering this vector space which is spanned by the partial derivative operators. So what we've now kind of discovered is that a vector should really be realised as a linear operator. Well, actually it kind of makes a little bit more sense to say the definition the other way around and really saying that a derivative, or a linear operator like a derivative on the manifold, it is a vector, not a vector is a derivative. So essentially what that's saying is that the algebraic structure which is generated by these d by dx mu objects, it has the algebraic structure of a vector space. And we can understand this because we know that derivatives are linear. You can take the derivative of two functions being added together and it splits up linearly. So we know, or we expect, that derivatives should behave linearly, and hence derivatives are vectors.